Evaluating limits analytically for piecewise functions. So first, let's just review really quickly, what is a piecewise function? Well, a piecewise function is a function which is broken up into intervals, with each interval having its own equation. So let's take a look at an example of a piecewise function. So here we have f of x, and this particular piecewise function is broken up into three separate pieces. So when our input values are less than 0, we're going to plug those input values into the expression x plus 2 to get our output. If our input values are in between and including 0 to 1, when we input those values, our output is going to be 2. And then when our input is greater than 1, we're going to plug our inputs into 3 minus x to get our outputs. So again, there are three different pieces here, but the pieces are connected at certain x values. So for example, we can see that our top expression is numbers that are less than 0, and then our second expression picks up right at 0. So it would be nice if the two functions were able to meet at x equals 0, but by what we're given here, we don't know whether that's true or not. Similarly, the middle function goes from 0 to 1, and then our bottom function picks up at 1. So again, it would be nice if our second and third function would meet at x equals 1 to create a continuous function. And if we do look at the graph of this, we can see that yes, in fact, these functions do meet creating a continuous function. So the first and the second function do meet at x equals 0, and the second and the third function do meet at x equals 1. And again, we have a third function. But these kind of like connector points, x equals 0 and x equals 1, we're going to refer to these as a values, based on what we're going to be going over in the next couple slides. So just keep that in mind. But anyways, if we were going to look at this function, and if we were going to look at it using the number line for interval notation, we know that we are going to have one function or one expression for all the values that are less than 0. We're going to have one expression or the outputs for all the inputs that are in between and including 0 and 1. And then we will have our third function for all inputs that are greater than 1. And now this is a great, nice piecewise function because it is continuous. But as we know from previous math experiences, piecewise functions are not always continuous. So that is where limits come into play. So how do we evaluate limits of piecewise functions? And for our first example, we're given a piecewise function with three pieces: 3x minus 1 when x is less than or equal to -1, x squared plus 5x when x is less than 1 but greater than -1, and 3x cubed when x is greater than or equal to 1. And the directions say find the limit as x approaches a from the left of f of x, find the limit as x approaches a from the right of f of x, and then find the limit as x approaches a of f of x. Now, in Calc 1, this is a pretty basic, fundamental calculus course, so most of the time these a values that we're looking at are going to be those connector values, so -1 and -1, and then 1 and 1. Now, the a values for which we're finding a limit, they don't actually have to be these connector values, but that's just the common concept that is being taught and tested in Calculus 1. So most of the time that'll be true, but not always. So pay attention to what values the limit is approaching. But anyways, we can see here that we're going to have two different a values. So to figure out what the a values are, or to figure out, let me take that back, we can figure out what the a values are. We can see that these two connecting are a equals -1, and then we can see that these two connecting are going to be a equals +1. Now, since we are trying to find the limit from the left, the limit from the right, and the two-sided limit, I usually find it helpful to draw a number line and then actually put my pieces on the number line. So we've determined that our a value is -1 and +1. And we know that when x is less than or equal to 1, we're going to be using the expression 3x minus 1 to calculate our output. When our inputs are in between -1 and 1, we're going to be using x squared plus 5x. And then when x is greater than or equal to 1, we're going to be using the expression x cubed to find our output. All right, so let's see. If we are going to be looking at our first a value, we can see that the limit as x approaches -1 from the left would be coming from this direction. So therefore, when we want to find the limit as x approaches -1 from the left, we would be using the expression 3x minus 1. I'm going to write this down in just a moment, but I just want to finish filling out this chart. Then if we were trying to find the limit as x approaches -1 from the right, we would be in this middle section here, so we would be using this expression to evaluate the limit. However, if we want to find the limit of +1 from the left, that also lives in this middle section, so we would also use this x squared plus 5 to evaluate the limit as x approaches 1 from the left. And then as you can see, if we would try to find the limit as x approaches 1 from the right, we would use the function 3x squared. All right, so now let's go ahead and let's evaluate all these limits. So for our first set, we're going to use our a equals -1 value. So that means we're going to be looking for the limit as x approaches -1 from the left, the limit as x approaches -1 from the right, and the limit as x approaches -1. Now, the most challenging part about evaluating limits of piecewise functions is choosing the correct expression to put in the limit. So for our first limit, we're looking at x approaches -1 from the left, and we've already identified that that's going to be 3x minus 1. So we'll throw that expression in there. To evaluate the limit as x approaches -1 from the right, we have also said that that's going to be x squared plus 5x. So we can throw that in there. Now for the limit as x approaches -1. Since this is a piecewise function, and since we have different expressions coming from both the left and the right, we don't have one single expression to put in here. So when that's the case, we just put f of x. And now we can just go to town and we can start solving these. We can see that the first two limits are both polynomials, and as we have learned in previous videos, polynomials are continuous, and for continuous functions we can use direct substitution. So that means it's going to be 3 times our a value, which is -1 minus 1, which is going to give us -3 minus 1, or -4. And there we have the limit as x approaches -1 from the left. We can do the same thing for x approaches -1 to the right. So this is going to be -1 squared plus 5 times -1. That will be 1 minus 5, which also equals -4. And then finally, we need to evaluate the two-sided limits. And let's remember, two-sided limit exists when the limit from the left equals the limit from the right. And wouldn't you know it, our limit from the left and the limit for the right here both equal -4. So therefore, our two-sided limit is going to equal -4 as well. All right, so we've taken care of one a value. Let's move on to the second one. So we're going to have a is equal to +1 now. And then we can set up our limits. X approaches +1 from the left, limit as x approaches +1 from the right, and the limit as x approaches +1. Now we just need to fill in the expressions that we're going to be using, and as we've already talked about, the limit as x approaches 1 from the left is going to be x squared plus 5. And the limit as x approaches 1 from the right, we've already identified is going to be 3x cubed. And since this is a piecewise function, we don't have one single expression for the two-sided limit, so we're just going to fill that in with f of x. And similarly to before, we can see that both of our one-sided limits are polynomials, which means they are continuous, which means we can use direct substitution. So we're going to have 1 squared plus 5, which gives us 1 plus 5, which gives us 6. Then the limit as x approaches 1 from the right. This is going to be 3 times 1 cubed, and I apologize, I just realized that I wrote a squared instead of a cube, so let's fix that. All right, so then 3 times 1 cubed is just going to be 3. Now onto our two-sided limit. Remember, the two-sided limit exists when the limit from the left equals the limit from the right. In this case, 6 does not equal 3. So therefore, this two-sided limit does not exist, so we can just write D, N, E. All right, great. Let's take a look at some more examples. Focused, it tells us exactly what limit to find, and the function we're looking at is just has two pieces. So this is a much more well-defined question and should be a lot more straightforward to solve. So we are looking at the two-sided limit as x approaches 3, so that means in order for us to analyze that limit, we first need to look at the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right, and that will allow us to determine whether or not this two-sided limit exists. Alright, so just like before, I find it helpful to draw a number line, and I'm going to put our a value in the middle, which is 3. And I can see here that when x is less than 3, the function we're going to use is x squared. When x is greater than 3, the function we're going to use is x plus 4. So that means when we approach 3 from the left-hand side, we'll be using x squared. And when we approach 3 from the right-hand side, we will be using x plus 4. Now, just like the last example, these are both polynomials, which means we can use direct substitution. So for our first limit, we're going to have 3 squared, which equals 9. For our next limit, x plus 4, that'll be 3 plus 4, which gives us 7. Now remember, in order for our two-sided limit to exist, the limit from the left to right have to equal, and 7 does not equal 9, so therefore this particular limit does not exist. Alright, so this next example is also well defined like the last one because it gives us the limit as x approaches 6 from the right of f of x. However, our function is a little bit more complicated here because it is a three-function piecewise function, or say piecewise function with 3 pieces. So now we're just trying to evaluate a one-sided limit here. So this one's nice and easy. We just have to evaluate one limit. But the difficulty comes with what's our function? Which one of these 3 pieces are we going to use? So, as always, I prefer to draw a number line. So I'm going to plot my a values of 1 and 6. I know when x is less than 1, I'm going to use negative 2x squared plus x plus 3. I know when it's between 1 and 6 is going to be 2x squared minus 3x plus 3. And when it is greater than 6 is going to be negative 3x minus 2. Now, our limit is looking for, as we approach 6 from the right-hand side, so that means we would be using the function negative 3x minus 2. So we'll throw that in here, negative 3x minus 2. We can use direct substitution because it's a polynomial. That's going to leave us with negative 3 times 6 minus 2, or negative 18 minus 2, which gives us an answer of negative 20. Alright folks, and there you have it. That is evaluating limits using piecewise functions.